Hello and welcome, class, to the lecture series I am here now pre-recording, posting on YouTube, etc., where I am slowly marching through in the fall of 2020, my first semester general chemistry course. So all of these lectures being pre-recorded all correspond to the class that I actually teach. Just realized I never actually brought my pen up. Here we go. Pen. So in the textbook that we are using, we are now entering chapter 2. I did go through, after filming, pre-recording, whatever, all of my chapter 1 lectures. I did go through now and actually update all of the pages for the 4th edition of the text that I am using. The reason why I'm saying that is because my actual, physical class, hey guys, the text that we are using is the 4th edition. It is the most up-to-date. It was just released this last summer. So now all of these page numbers, all of the problems, section review, suggestions, everything, tables, everything should be updated for the 4th edition. So you don't have to go through and find approximate pages. This is exactly where they're going to be. Between the pages that I have listed here, we are now going to be discussing subatomic particles. So atoms are made of things. The particles creatively were named subatomic particles because they are less than, in terms of mass at least, the total of the atom, right? They comprise the atom. So in chapter 1, everything we talked about was more foundational, general terms, definitions, algebraic processes. Now we're actually going to be starting the meat of the semester. We're actually going to be talking about the chemistry, atoms first. All right, so the theory of the atom has a very long and rich history, so I am just going to condense all of that into basically the two main philosophers / scientists that we attribute the atomic theory to. First and foremost, we have the Greek philosopher Democritus, who was alive from 460 to 370 BCE. The Greek philosopher Democritus is the one who is attributed with the novel concept of what he referred to as the atomos. By definition, the atomos, by Democritus's thinking, was an indivisible particle of stuff. Now, his idea of the atom was very different than ours in the sense that, what he believed was that, let's say you took a tree, you chop it down, you keep grinding down the wood to finer and finer particles, and you would eventually find an atom of wood. So he didn't think of elements in the same way that we think of elements today, but he did believe that if you were to take a physical object and try and break it down, there would be a point where you would no longer be able to break it down. That piece of matter would become indivisible at a point. The, his philosophy, his theory of the atom, his hypothesis, whatever you want to refer to it as, was a very contentious viewpoint back in the day. There were a larger number, right, a majority of philosophers who did believe that matter was infinitely divisible. So Democritus was kind of the odd man out here. He, for no real reason other than the fact that it became difficult to cut things in half or grind things down, macroscopically, that was what he was going off of. At the same time, he ended up being right, as history has since, demonstrated. So the rest of the philosophers who believed that everything that matter was infinitely divisible, for whatever reason, there were many different postulates as to why things could be, in theory, infinitely divisible. Democritus ended up being correct. And so the atomic theory was really picked up by John Dalton, who was alive 1766 to 1844. Now, his atomic theory was partially based off of Democritus's atomic theory. John Dalton was a very well-read man, knew a lot of the great old Grecian philosophers, and based off of the work that he was doing, which we will be getting into more in the spring semester, he was a gas laws scientist. And based off of his observations of the behavior of gases, he started to, he was inspired by Democritus's work and some of these, burgeoning atomic theories, and then decided to write his own based off of his own observations. Now, John Dalton's atomic theory comes in 3 premises. 2 of these have since been proven incorrect. So here's a really good testament to how, right, we have really great ideas, really great postulates, really great hypotheses based off of evidence that we have sitting in front of us. But as more and more evidence comes out of the woodwork through scientific experimentation, we have to revise our thinking a little bit. But it's still important to acknowledge these 3 premises, because these 3 premises are what we then have built our current atomic theory off of. So the first premise was that everything is comprised of indestructible atoms, right? Everything is comprised of the atomos, the indivisible. Second point is that all atoms of a given element are identical. So every like lithium atom is the exact same as another lithium atom, is the exact same as another lithium atom, etc. Whatever the element type is, every single atom of that element, or every single, as a result, molecule of a certain compound should be the exact same. Point number 3, atoms combine in whole numbered ratios. So we have things, again, like H2O. There is no such thing as H1O1/2. You can't have 1/2 of an atom. These atoms must exist physically in their molecules as whole discrete units. All right, so what we're going to be doing then in Chapter 2, at least for the first 2 parts of the lecture series in Chapter 2, is addressing which things John Dalton got right and which things he got wrong. So what we're going to do is start with premise number 1, everything is comprised of indestructible atoms. The reason why this is incorrect, launching us into the rest of the lecture for part 1, is because we have since found, especially in more recent years, starting kind of the 1800s, moving into the 1900s, that atoms actually are destructible. Atoms are made up of 3 subatomic particles known as the electron, the proton, and the neutron. So what we're going to be talking about here today then, continuing through part 1, is the discovery of these 3 subatomic particles, how we were able to isolate them, put them together then to give us a more accurate understanding of what an atom is. So in order to move into this lecture, we must first recognize that in the late 1800s, what we were going through was an era of science that was completely obsessed with radiation. So we in science, we scientists, or those with a scientific mind, or mindset, right, inclination, tend to, like not just now, but throughout history, once there is a new technology, take that technology, throw it at stuff, and see what happens. So for instance, humans back in the day learned to harness fire. And those who were very curious about fire and how it interacted with the world around us took fire and combined it with stuff. What can we burn? And when we burn it, what do we get on the other side? Through experimentation with fire, not only did we determine which things were flammable, like wood, and could be used as fuel, but we also discovered that certain objects, certain pieces of matter, could either be combined together to give us something amazing and new, like bronze, which started the Bronze Age, or could be separated by fire. Things like iron ore, which then can be smelted, purified down, giving us just liquid iron, which could also be cast, and that discovery is what started the Iron Age. So we used fire, threw it, combined it with stuff, right, and found some great new technologies which really helped like mankind and society to advance. Same thing happened with electricity, and then right in the 1800s, what was really happening was the discovery of radiation. And so we, in much that same mindset as humans have always been, curious beings, took that radiation, combined it with other things, other pieces of matter, and saw what happened. All right, so what is radioactivity? Why were we so obsessed with radiation? Well, first and foremost, it was a new discovery, right? New source of energy. And what's really awesome about radioactive materials is that they just emit energy spontaneously. So the discovery of radioactive materials, namely also the discovery technologically of how to harness and control these materials, is what led to a rush for like new means or a like new source of energy. Right, and we're still kind of on the hunt for energy nowadays, but the awesome thing about radioactive materials is that the materials just emit energy. They just give off energy. And so the thinking back in the day was if we could find a way to harness this energy, we could use it as a renewable source, get away from coal, get away from other sources. If this material just gave us energy, then why aren't we using it? Well, as we have since learned, right through history and a number of disasters at nuclear plants, radioactive materials give off energy spontaneously because they decompose. And this decomposition can be difficult to control at times. If like sensors go off, if things go wrong, if conditions aren't right, you can get what we know as a nuclear meltdown. So, every pro has a con. Every light side has a dark side. The dark side of radioactive materials and harnessing them for energy is that it can be incredibly dangerous when we try to do so in bulk. It's not to say that we shouldn't, it's just to say that's why we haven't 100% switched to nuclear energy. It's because it can be incredibly dangerous. All right, so radioactive materials, how they release this energy, what happens if we have, as we can see in kind of this diagram down below, some type of radioactive source. What this source does is breaks down into like lesser particles. In the process, it releases 3 different rays. We have alpha rays, beta rays, and gamma rays. Now, the radioactive materials were also found to not be able to pass through lead. Lead is very good at blocking radioactive decay, so if you take a piece of radioactive material and put it in like a lead box where there's just one little hole inside of that lead box, the radiation is only going to be able to come out of this one point. All right, in doing so, we've been able to take our like radioactive energy, really like, again, intelligently focus it in one direction. So we've been able to like break down, understand, test what the radiation is, what it's made of. And electricity and magnetism was also a very a very hot spot. It was very, how do I say this? Electricity and magnetism was a focus of scientific study. I mean, that's the easiest way to say it. It was also a relatively new technology. We were still interested in what it had to teach us. And so if we took radiation, combined it with electricity or electrically charged plates in this case, what did we find? Well, we found that the alpha rays and the beta rays were deflected or interacted with the electric field that was generated by these electrically charged plates. The beta rays, we can see kind of shifted upwards towards the positive plate, and the alpha rays shifted downward toward the negative plate. What this told scientists and still tells us today is that the beta rays and the alpha rays, yes, are very high energy, but they are also made of matter. In order to interact with an electric field, like how these beta rays and alpha rays are demonstrating here in this diagram, they need to be made of matter. So that means that beta rays are made of a particle, alpha rays are made of a particle. The beta rays must be negatively charged if they're interacting with the positive side of this plate, right? Because positives and negatives attract. So these beta rays are made of negatively charged particles. And the alpha rays must be made up similarly of positively charged particles. All right, so we have 2 different rays, the alpha and the beta, which are comprised of stuff. They're comprised of matter. The gamma rays, which we can see straight through the middle, this third type of ray that is separated out from the electric plates, resulting from the radiation from this radioactive substance, just goes straight on through, right? There's no deflection, there's no attraction to the positive or attraction to the negative. Since there is no interaction with these charged plates, we can conclude, as the scientists also concluded back in the day, that the gamma rays are not made of matter, they are made of pure energy. So energy like this, like the gamma rays, can just shoot straight through electric fields, not become attracted or deflected, because they themselves do not have any type of charge. All right, so we have the alpha rays, the beta rays, and the gamma rays. So over the course of this conversation, we are going to continue to discuss the beta rays, the alpha rays, and the gamma rays. Namely, what are they made of? What are these particles here? And that is exactly what the scientist J.J. Thomson and his graduate student R.A. Millikan wanted to find out. What were the beta rays made of? So they constructed a number of experiments that we will break down in the up-and-coming slides, right, as telling a story. And what they discovered in performing their experiments is that the beta rays are comprised of a particle that was less massive than the smallest atom. Right, so at this point in history, atoms had been known. The atomic theory, Dalton's atomic theory, had been widely published. And so for these guys to find a particle that was less massive than the smallest atom just completely broke our understanding of the material world around us. All right, so what was their experiment? How did they find this particle? How did they find out that beta rays are made up of a particle that are less massive than hydrogen, which was the least massive atom known at the time? So they were studying what are known as cathode ray tubes. If you've ever come into contact, like possibly your parents had one, your grandparents maybe even still have one, and an old CRT TV, those TVs or those old screens are comprised of cathode ray tubes, right? CRT. Cathode ray tubes function via electricity. We just have electricity running through these tubes, all depending on how much electricity or the construction of the tube. We can generate different colors, and that is how then each of those individual tubes function as a pixel on the TV screen. So nowadays we have LED TVs, like flat screen TVs are LEDs, crystalline nature. We don't have cathode ray tubes inside of them anymore. And that's namely just because LEDs can get to be smaller. Cathode ray tubes cannot offer us the same resolution as like a modern flat day screen. But each of the old pixels, if you ever have the chance or have had the chance to see an old CRT TV, you can actively see each of the individual pixels if you sit really close. All right, so if we're looking at just an individual cathode ray tube, we can use it in conjunction with, again, these kind of electric plates, placing them around the cathode ray tube to find a charge to mass ratio of the beta rays as they're coming through the tube. So in the diagram, what we have illustrated here is the cathode ray tube itself. There are, like the cathode rays inside of this tube are being generated from this negative plate and this positive plate. So we have electricity moving in. The negative plate being separated from the positive plate really forces these beta rays to be, or cathode rays, the two are synonymous, cathode ray and beta ray. The beta rays shoot through the tube from the negative to the positive, right? Because beta rays are negatively charged or comprised of negatively charged particles. They're going to be attracted by this positive plate, which will pull them through. There's a tiny little pinhole here, so the beta rays are going to travel through that tiny pinhole, coming out here. Because again, they are negatively charged, this positive plate's going to attract them, pulling them upwards. Opposite charges attract. And all depending on the magnitude of the electric current that was coming through the positive and, the negative plate, the scientists J.J. Thomson and R.A. Millikan were able to conclude that the charge to mass ratio of the particle, of these beta ray particles, must be 1.76 times 10 to the 8th coulombs per gram. So again, it is a charge to mass ratio that we are looking at. Right, so they were the ones who reasoned that the beta rays, or not reasoned, but helped to solidly conclude that these beta rays are comprised of negatively charged particles, and either they have a very large charge, right, because 10 to the 8 is a very large number. So either they have an incredibly large charge, or they must have a very small mass. Well, in order to really parse out, separate the charge, like the magnitude of the charge from the magnitude of the mass, R.A. Millikan, the graduate student, designed another experiment kind of following up from the cathode ray tube studies, which is now famously known as the oil drop experiment. So he was pretty clever in trying, or in how he set up the experiment for separating, or finding rather separately the charge, and then from that calculating the mass. So the experiment itself physically is set up in kind of a way that's similar to this diagram that's here on the right. First and foremost, there was an atomizer present. His original quote-unquote atomizer was really like a very, it was like a perfume bottle that sprayed a very fine mist. And the mist that he sprayed inside were like oil droplets. So he was just spraying a fine mist of oil droplets in the top section, this upper section of this container. And due to gravity, the oil droplets would slowly fall on down. Now there was a very small pinhole, which we can kind of see right here, in the plate below. So as the oil drops kind of fell through, they were hit by an X-ray source. So they were given a charge. These particles were given some type of electric charge. Now the lower floor of the upper chamber / the upper floor of this middle chamber was a charged plate. It was a positively charged plate. And underneath we can see here a negatively charged plate. And so what Millikan did was, as these particles, these oil droplets, were falling from the top section down into this middle section, being zapped by this ionic ray and given a charge, is he would adjust the magnitude of the charge on this upper and lower plate until he found the perfect charge that caused the oil droplet to stop moving. The reason why the oil droplet stops moving is its charge equally matches that of the positive plate and the lower plate. So because this charged particle equally matches the charge of the plates above and below it, it's not overall attracted to one versus the other. It just ends up kind of hovering in midair. And so from his experiments, he was able to conclude that no matter exactly how charged the particles were, these oil droplets as they came down, their charge was always a factor of 1.602 times 10 to the negative 19th coulombs. So the charge of these particles could vary. However, again, the charges were always a factor of 1.602 times 10 to the negative 19th. So he reasoned that if one particle was more charged than another particle, then what that means is that it had more of these like tiny negative particles on top of it. And again, as you like increase the number of these negative particles that were like sticking to the oil droplet, the charge would increase as a factor, again, of this 1.602 times 10 to the 19th. So if we take this charge that he found and combine it mathematically with the charge to mass ratio from the previous slide, which again was that 1.76 times 10 to the 8th coulombs per gram, 1.76 times 10 to the 8th coulombs per gram, right, is equal to this charge that he just found, 1.602 times 10 to the negative 19th coulombs. Solve for x, we can figure out what the mass of this very tiny particle is. And in doing so, the mass of this very tiny particle that comprised the beta ray was found. The charge is equal to 9.109 times 10 to the negative 28th grams. So just to give a little bit of context for like how small this number is, this number is 5 thousandths the size, 5 thousandths the mass, right? So 5,000 times smaller than the mass of hydrogen, approximately. This is super ridiculously tiny. And when the results were first found and published, no one believed them. Like even J.J. Thomson himself had a little bit of issue with this finding until, you know, like just scientific experiment. He was present for the experiments. They kept adjusting the charges of the plates. They kept trying to fix the atomizer. Like they were convinced that they must have been wrong until just time and time again, scientific experiment kept giving them the same results. They kept finding the exact same charge of this tiny particle. They kept finding the exact same mass of this tiny particle. And so they published their results, and like, again, the world was kind of like have an issue with it, but there were also a fair number of scientists who did not have necessarily an issue with Thomson and Millikan's results, but rather let their imaginations run wild. What could this mean? And what Thomson thought it meant was that Dalton's picture of what an atom was must have been slightly wrong, right? Not quite correct. Mostly there, but kind of off. So Thomson offered his new picture for what an atom should look like, or rather what an atom, according to him, did look like, and this version of the atom is known now as the Plum Pudding model. In Thomson's vision for what, like how an atom was constructed, these tiny little particles, these particles that were less massive than hydrogen, had to, in his mind, be a component for what an atom was made of. So atoms are known to be charge neutral, and this tiny, tiny particle, which he reasoned is inside of an atom, which he started calling an electron, has a negative charge, right? That very tiny, charge that we found, but it was still a negative charge. There must be a positive component for this atom as well in order, again, for the total thing to still be charge neutral. So the Plum Pudding model, his picture of an atom, we can kind of see illustrated here. What he imagined is that all of those tiny little negative particles that he found, again, the beta particles, which he then started referring to as electrons, have a negative charge. He knows that they are physical particles because we had found the physical particles by this point, right? He had isolated what he then referred to as the electron. Well, the positive piece that he imagined in the atom must have been this kind of positive, diffuse, net. Some type of an electric force field. So his Plum Pudding model, he then reasoned, since we have these positive or negative electrons that we knew existed, they were just kind of embedded in this kind of diffuse positive sphere, aka some type of electric field. All right, so how he was inspired by this, or rather how he was inspired and came up with this picture and why he called it the Plum Pudding model is because of what the British eat, the plum pudding. So Thomson was a British man, and here's my own headcanon that Thomson was eating dessert one night. This is the image of what plum pudding looks like. It's not pudding as we Americans think of it, a Jell-O mold kind of plum pudding thing, or puddings kind of thing. Instead, it's a cake. So puddings in Britain are known as what we would say cakes. And we can see that there's this kind of cake that's illustrated here, and each of these little nuggets of fruit inside are little dried out plums. And so what Thomson envisioned was that the cakey part, cake, was equal to that positive force field, and that all of the plums inside, the plums, are the electrons. So we just have a lot of positivity, kind of roughly in the shape of a sphere, and all of the electrons as a real physical particle are embedded inside of the cakey bit, inside of that positive force field. So this is what Thomson envisioned an atom looked like. All right, Thomson was not, again, the only one who started, believing in what his results were. He had a good friend by the name of Ernest Rutherford, who is a scientist out of New Zealand, also working in England. He was either working at Oxford or Cambridge. Editing Dr. Billman, please insert on the screen, where was he working again? I'm trying to remember, it's not coming to me. But he was working, in science. He was a physicist by trade, and what he decided to do was try to prove his friend, J.J. Thomson's Plum Pudding model correct. So he designed an experiment with the help, again, of his graduate students, Hans Geiger and Ernest Marsden, and in doing so, accidentally discovered what we now refer to as the atomic nucleus. All right, so his experiment is famously now referred to as the gold foil experiment. So what Rutherford did was shot alpha particles, aka an alpha ray, that positively charged energetic ray made of particles, at a very thin piece of gold foil. If the Plum Pudding model was correct, all of these positive particles should in theory have shot straight on through the foil. The main reason that he thought this way is that if the Plum Pudding model was correct and the positivity in an atom was just kind of a loose, nebulous, right, again, kind of electric field, blah, 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 there's no physical positive resistance for another positive particle that should in theory shoot straight on through. There would be some minor deflection just due to electric field interactions, like he in theory was expecting to see the positive particles, all depending on the exact angle of contact with this spherical atom, might have seen like a little bit of deflection by the like positive field, but for the most part you would see everything, all of these positive particles just shoot straight on through. However, again, upon repeated experimentation, he found that the particles did not shoot straight on through, but rather some were deflected by larger degrees than what he was expecting. In fact, some of them even deflected completely backwards, which just totally baffled him. Rutherford was then recorded to say, "It was as incredible as shooting a cannonball at a piece of tissue paper and having that cannonball bounce back." His line of thinking, again, Thomson was his friend. He was trying to help his friend out, design a scientific experiment to help support his friend's picture for an atom. But at the end of the day, he ended up finding the exact opposite. He ended up disproving his friend's theory instead. So again, Thomson's model, we have all of these little negative electrons embedded in this diffuse positive sphere. The alpha particles, alpha rays, coming like from one side, if this is like the perpendicular of the gold foil, these alpha rays shooting through and towards this gold atom, in theory, should have just passed right on through this diffuse positive sphere. But instead, Rutherford's model found that we had some deflection, which means inside of the atom there has to be some type of positive particle, just like how there are pieces of negativity. And he reasoned that in order for these alpha particles to be able to deflect back, especially at the extreme angles, like back towards the device that was shooting off these alpha rays, the positive particles inside of the atom must be condensed in some type of like central location inside of the atom. He referred to this as the nucleus. And so, building off of J.J. Thomson's Plum Pudding model, Rutherford decided to come out with his own picture of the atom. We now refer to this as Rutherford's nuclear model. He reasoned that in order for a majority of the alpha rays, because to go backwards to a previous slide, a majority of the rays we can see here kind of illustrated hitting this like detecting like sheet on the backside, most of the rays did go through. Well, he reasoned that if there is some type of positive particle inside of an atom, it must be centrally located and the rest of the atom is more than likely empty space. This emptiness is what allowed for the space, gave the space, which allowed the alpha particles to just shoot straight on through. Most of the mass inside of the atom, therefore, must be contained in the core of the atom, the nucleus, which then he said the positive particles inside of the nucleus must be, should be called something, and he called them protons. Third bit of Rutherford's nuclear model is that, well, if the nucleus is in the center and the electrons, which can be seemingly added and removed, all depending on what the electric field around it is, how many spare negative particles, if the electrons can just be added and removed, then the electrons have to be separate from the nucleus, and they more than likely are orbiting the nucleus, much like how planets were known to orbit the sun. So here we have kind of a cartoony illustration of what Rutherford's nuclear model is. And in fact, this is still the most colloquial vision or common vision, cultural vision of what an atom looks like. Like if you walk down the street, those kind of reportive interviewers, popping up on the street, getting people's perspectives. If you ask a random person on the street to draw what an atom looks like, they're going to draw some type of nucleus in the center, and they are more than likely going to draw a couple of electrons, like we see in blue, labeled here, electrons circling around the nucleus. It's just a very pervasive image of what an atom looks like, even though, spoilers, we now know that this is incorrect. All right, so another way to, though, emphasize exactly how much empty space is inside of an atom, according to Rutherford's nuclear model, because, right, to go backwards, here we see the nucleus being, pretty large. There's some empty space, but not a ton of empty space. The electrons themselves are also, relatively big. In order to get a really good idea, though, for exactly how vastly empty atoms are, and this is still true today, is imagine that you are standing in the halls of a very large church like this cathedral pictured here. A mote of dust floating in the center of the room is the nucleus. And the exterior, the shell of the building, is the closest electron. The atom is so incredibly empty that if we were to take an atom and scale it up to the size of a building, that building would be mostly empty. Right, so we commonly think of atoms as very small solar systems. Again, most people still think or picture an atom like how Rutherford did. But a question that I want to leave you with until we at least get to the point where we can actually answer this question is, if there is a positive nucleus inside of an atom, and the shell, the exterior, is made up of negatively charged electrons, and we know that positives and negatives attract, why don't electrons just fall into the nucleus? What is stopping these two particles from joining together? Now, we are going to be answering that question, but it's something that I just want to leave you with puzzling for a couple of days. Sometimes it's good not to have the answer right away. Sometimes it's nice to be able to think and see if you can't figure out the answer for yourself before we get there. So yeah, that's a mystery, at least at this point in our lecture series. Why are they not connecting? Why is the atom mostly empty space? All right, but there is still one more subatomic particle to discover. Inside of the nucleus, we, up until this point, right, with Rutherford's nuclear model, know that there are positively charged protons inside. In studying the very small atoms, particularly their masses, a scientist by the name of James Chadwick was observing hydrogen versus helium, where hydrogen was at the time then discovered to have 1 proton, versus helium has 2 protons. There is a charge balance in these two atoms that is a 1-to-2. So in theory, right, if the protons are what provide most of the mass in the atom, according to Rutherford's gold foil experiment, the mass ratio should also be 1-to-2. However, through experimentation, it was actually determined that the mass ratio of hydrogen to helium is 1-to-4. In other words, helium was 2 times more massive than what, in theory, was predicted. So why was that? Well, through further experimentation, what James Chadwick found, what he reasoned, is that the extra mass must come from another subatomic particle, a third to complete the trilogy, a third to complete the trio. He called this particle a neutron. This particle, in theory, and as we have since confirmed through experimentation and confirmed, did I just say confirmed twice? We've confirmed through experimentation, yes, that this particle known as the neutron is nearly identical to the proton in terms of mass. However, it does not have a charge. It not having a charge is exactly the reason why it took so long to discover the existence and isolate, right, the neutron from the other subatomic particles. Up until this point, we've been using things like electric fields to separate the positive from the negative. Well, if you have a particle without a charge, it's not going to be attracted either way, and had up until this point with James Chadwick's work just kind of been overlooked. So he was the one who clued in to the existence of the neutron, and since it is a neutral particle, right, neutral in charge, that is where it gets its name, the neutron. All right, so table 2.1 in our textbook, as is also depicted here, this recreation of table 2.1, we have a summary of all of the pieces of information that we now know about the subatomic particles. Particles being the electron, the proton, and the neutron. And in the 100+ years since this information was found, gathered, kind of like collected together, we have not found an additional subatomic particle that exists inside of the atom. So this is it. This is the comprehensive list. We have the electron with a very tiny mass, very tiny charge, sorry, that charge is negative, and the proton has the equal yet opposite charge. So oftentimes we represent the charge of the electron and the proton with their relative charges, a -1 and a +1, even though in terms of absolute magnitude in the unit of the coulomb, the charges we can see here are very, very small. Neutron, perfectly neutral, meaning that it also has a perfectly zero relative charge to both the other things, the electron and the proton. Now the masses are also very, very small. Again, this very, very tiny mass was what clued us in to the existence of the subatomic particles in the first place. The electron having a mass in grams of 9.109 times 10 to the -28. And we can see that the masses of the proton and the neutron, yes, again, are very small, but they're approximately equal to one another. So the mass of the proton is 1.673 times 10 to the -24. And the neutron, again rounded to kind of the thousandths place, is 1.675 times 10 to the -24. Now the relative masses, which we can rewrite in atomic mass units, where, if we look all the way down here, the unit of the AMU is standardized to the carbon-12 atom. So that's why these numbers are not exactly like equal to 1, like the mass of the proton and the mass of the neutron's not exactly equal to 1. It's because atomic mass units are standard to something else. They're standard to the carbon-12 atom. So relative to the carbon-12 atom, the electron is 5, let's see, this is the tens place, hundreds place, thousands place, 5 10,000ths of an atomic mass unit. The proton and the neutron are both approximately equal to 1. They are 1.0073 atomic mass units and 1.0086 atomic mass units. So again, we can see exactly how small relative to even the proton the electron is. And spoiler, also to give a little bit of context again for like how incredibly tiny the electron was and why we were so befuddled in the first place, the element of hydrogen is comprised of, now we know, 1 electron and 1 proton. So the element of hydrogen, which was the least massive element, and still is the least massive element on the periodic table, has a mass that is approximately equal to that of the proton. So when the electron was discovered and this incredibly tiny mass was discovered, that was what started this whole cascade. That's what started us on this journey of being able to discover, looking for, and finding all of these subatomic particles. All right, to reiterate though, the discovery of the atom, the subatomic particles inside of the atom, like, yeah, we had Thomson's Plum Pudding model, then that was revised with Rutherford and his gold foil experiment, but even then, when having so much experimental evidence in support of this conjecture, the idea that we had a positive nucleus and the electrons on the outside, a lot of the scientists in the fields of physics, chemistry, etc., were incredibly skeptical of the construction of the atom that had been proposed thus far, honestly based on the exact question that I left you guys with earlier. If there is a positive nucleus inside of the atom and a negative particle on the outside, should these things not be attracted to one another? According to classical physics, right, the idea of positives and negatives attracting, of like force is equal to mass times acceleration, parabolic arcs, etc. An electron, even if it was in orbit separated from this positive nucleus, should in theory emit electromagnetic radiation. In other words, it should lose energy. As it's moving around, this electron would move or lose energy. As it loses energy, it should then, in theory, be spiraling in tighter and tighter towards the nucleus until the two met, right? We would have negative and positive touching one another. We can get like a really good visual for this if you've ever had two separate or like separated magnets and spun them around each other, they will spiral into each other, right? We have this attraction even at the macroscopic scale. So why did the atom not collapse? This became known as the collapsing atom paradox, and it took a while until physics had advanced enough for us to be able to understand why it was that the electron did not fall into the nucleus and why the atom did not collapse. So again, this is where I am leaving you guys though with kind of that puzzle. Let yourself think it over. Let the strangeness wash over you, because the atom, especially when we get down to the quantum level, which is where we are going to be going in chapter 3, it gets real weird. All right, so as we can see there, I just hit next, expecting there to be a section review. There is no section review following the qualitative story that I have presented you today. So just to move backwards, yeah, collapsing atom paradox. This is where I'm leaving you guys for the day. So if you have homework, do your homework. And until next time, class is dismissed.